Okay, let's talk about the relationship between Ka and Kb. For a conjugate acid conjugate base pair, the Ka times the Kb equals the Kw. Remember, Kw is the 1 times 10 to the negative 14th number. Therefore, the larger the Ka, the smaller the Kb will be. And that is, for example, if we know the Ka for acetic acid, we could determine the Kb for the acetate anion, which is its conjugate base. Very similar to pH and POH, we can have a pKa and a pKb, where the formulas look very similar. Negative log of Ka equals is equal to the pKa. Negative log of Kb is equal to the pKb. Very similar to pH and POH. And we can say the pKa plus the pKb equals the pKw, which is pKw is 14. So the pKa and the pKb will add up to be 14. So let's say we've got formic acid, and its Ka is 1.8 times 10 to the negative 4th power. We will know the Kb in the formate anion, and then therefore what is the pKa and the pKb. So let's take a look at that. Let's look at the relevant information. So remember, if we ionize this, again, I'll just omit the water for simplicity's sake. We're going to lose this acidic hydrogen. This is a covalent hydrogen that won't be lost. So CHO2 negative plus H plus. So this is its conjugate base, the formate anion. So if we know that's the Ka, then we know Ka times Kb equals 1.0 times 10 to the negative 14th. So then Kb is going to equal 1 times 10 to the negative 14th divided by the Ka, 1.8 times 10 to the negative 4th. And we should be able to get the Kb by running that through our calculator. And so we're going to get 5.6 times 10 to the negative 11th. And so that'd be the Kb for the formate ion. So what equilibrium does that represent? That would represent the formate ion acting as a base. That is, it reacts with water, and what you would get is the formic acid again plus a hydroxide. So the formate acts as a weak base by reacting with water. And so the Kb for that reaction is what we just calculated, 5.6 times 10 to the negative 11th. We got two more things to calculate. We're going to have the pKa and the pKb, so negative log of Ka. So that's going to be negative log of 1.8 times 10 to the negative 4th. And so we're going to run that through our calculator. And we'll get 3.7. Now I could do a very similar calculation since I calculated the Kb, or we could use the pKa plus the pKb equals 14. Since we haven't used this equation yet, I'll go this route. So the pKb is going to equal 14 minus 3.7. And we'll call that 10.3. And we'll treat that 14 as a more or less exact figure so we can get the tenths place. It's not technically exact, but we'll go ahead and keep the tenths place, so we can call that 14.0 if you really prefer on the sig figs. But then we got there 10.3, 3.7, 5.6 times 10 to the negative 11th, and those are our answers. So if we look at this table, we can see the relationship between Ka and Kb. For a strong acid like nitric acid, there really isn't a Ka because it's a one-directional reaction in order to be extremely large. But if you got a conjugate base for a strong acid like nitrate, it's not really a base. But if you got HF, 1.8 times 10 to the negative fourth, the fluoride ion is a very weak base, but a base nonetheless. Something that's more in the middle, 1.8 times 10 to the negative fifth. For acetic acid, the acetate ion is 5.6 times 10 to the negative 10th. Carbonic acid, 4.3 times 10 to the negative 7th. Bicarbonate, 2.3 times 10 to the negative 8th. So the stronger the acid, the weaker the conjugate base. By the time we get down to hydroxide, it's not really an acid at all, right? If you force it to lose one, the conjugate base would be oxide, but oxide is a strong base. Any base stronger than hydroxide, where hydroxide would be its conjugate acid, is a very strong base and will react with water in such a way as to form hydroxide.